have the pleasure to announce the last but not least speaker on this stage now, who is called Iftikhar Ahmed. Iftikhar, you're the quantum lead at Capgemini Invent. And so you look a lot into activities around go-to-market, the go-to-market stream for public tenders, for Capgemini's Quantum Lab, and you have a background in industrial engineering with a focus on mechanical engineering. And you will be presenting to us today an end-to-end approach to integrate and implement quantum resources into a hybrid R&D process, with a particular focus on life sciences and drug discovery. Iftikhar, welcome on stage. Thanks for being here.
Yeah, thank you very much. So I want to add one more thing to the kind of introduction, which was that what I have also been doing and what is part of I have been part of the Quantum Lab since its inception, and was part of our thinking around how do we actually create value out of quantum. And I think that's a question that all of us have asked ourselves at some point. Everybody who works in quantum has asked this question. And what I want to present really is how we as Capgemini developed our approach to that question and how we can answer that. I should mention right away that I was meant to present together with an esteemed colleague from GSK, who sadly, because of some scheduling issues, couldn't make it. So we wanted to go a bit more deeper into a specific project where we use this approach with GSK together. So I will still mention some of the points and the main learnings out of this project, but I would implore all of you to have a look at the research paper that we published together, Capgemini and GSK, about that project, which is available, and as I think is a very interesting read. So, to understand how we got to the approach that we got to, it's important to go back a few years to when the Quantum Lab started and when we started thinking about what we need to do in the space of quantum. What we did was we went out and had a lot of conversations. So we went to a lot of the industry leads, we went to a lot of the industry, big industry companies to see what were they doing with quantum. And we asked the simple question, how do you generate value out of quantum? And what we saw a lot in the market was something that we like to call pokitis. And that's something that's not specific to the quantum market. And we should mention that that happens in AI, in the AR market. You see that in every innovation technology market, which is basically that a lot of companies were doing POCs, and a lot of different POCs. And I should mention very interesting POCs, which is the case. There was a lot of interesting work out there. But what was missing of all of that was a strategic roadmap behind that. So how do you create value in the long term? How do you actually bring that POC into a working end-to-end process so that you have some value day to day, and what's the roadmap behind it? And with quantum, what was even more interesting was that some of those POCs were talking about use cases that the hardware to actually implement them in a meaningful way was still 10 years out. So that was something that we really took on board and started to think about, okay, what is an end-to-end process that we can actually think about that also has some value in the midterm, in the near to midterm. And when doing that, or before I actually go deeper into our approach, I should also mention where we were coming from, because that's very important to the approach itself. So Capgemini is a huge company which has very many different parts, but the Quantum Lab actually came out of the R&D part of the company. So Capgemini has a huge arm that works in R&D. There are hardware engineers, there are ML teams, there are scientists all over the world working in research labs and working in R&D departments to really figure out the solutions for the questions of tomorrow, and to really figure out how they can use data-driven approaches to find better solutions to the biggest questions that are out there. And when we started looking into this into quantum, we really came out of that part of the company and we're thinking about, is there even value in quantum for this, for the R&D departments and for this part of the company? Which was an interesting approach. So we didn't ask the question is what is the value? We asked the questions, is there even value? Because that was not our main business. Our main business was R&D, and we really were thinking about how we can make that business better. And so with that in mind, we really started looking into the quantum field, and what we found is something that all of us have realized at some point, which is that quantum computers are slow, quantum computers are noisy, quantum computers are small scale. So something that all of us are hoping for, like quadratic speed-ups and such, is still very, very far away. You could argue that we won't see quadratic speed-ups really in this decade. So the question that we then had to ask ourselves is like, where is actually value in the quantum field? And what we kind of zoned in on and where we saw a lot of opportunity was the space of chemistry. Because the chemistry space was one that was already where we were already actively very involved, but also chemistry and material science really are the building blocks, one of the main building blocks for some of the biggest industries out there. For aerospace, for life sciences, for climate tech, for many industries, there are so many R&D questions tied to the chemistry space where we see huge roadblocks coming on ahead. And that's where we then decided that that is a very interesting field where quantum could actually help us think about solutions. And that's how we decided on where we wanted our approach to start. And then when we came back to the drawing table and started thinking about the approach itself, there were three main principles that we wanted to adhere by. Basically making sure that this idea that we had of an end-to-end approach really is implemented. And those three principles, the first one really started with that we didn't see quantum as a replacement technology. So quantum was for us just an enhancement. It was just meant to enhance what was already there, the R&D life cycles, the R&D pipelines that were already there. How do we enhance them into something or use quantum to do something better? Then we also wanted to make sure we got the most out of the technology. Obviously, we mentioned that quantum computers, the hardware is still very nascent, very in the beginning, not very fast yet, but there is obviously being very good work done in regards to software, how we can create noise reduction, error mitigation, and so on. And a lot of those companies have also presented here and shown all their work. So we wanted to make sure that when we use our approach, we use it with the best possible outcomes and the best possible hardware. And then the last part really was about the flexibility and the scalability of our approach. We wanted to make sure that this approach is scalable, that it's not something that's bound by or vendor locked by a specific vendor, but that we come up with something that's abstract enough so that we can reuse it in different industries but also with different partners to really over time keep building it up and building something that scales with time. And doing all of that, we came up with this quantum-centric data-driven approach to R&D. And basically there are three main parts to this approach in itself, which is the embedding part, the feature extraction part, and then the data-driven modeling. The embedding part is really the core of this approach. And what the embedding part really includes is looking at the chemistry of whatever you want to look at or whatever the specific use case is that we are talking about, and looking at the chemistry and understanding where are specific molecules and specific features or fragments of those molecules that have some descriptive value of how they react, how they interact with each other. So that was a very much a quantum chemistry question, where a lot of quantum chemists work on to understand and use embedding models to understand how can we actually extract some information out of those molecules, what can we simulate that will give us some information about the behavior, about the characteristics of a specific molecule, of a specific fragment of a molecule. Then we use that and bring that into a time evolution or a Hamiltonian simulation, and basically put that on a quantum circuit to get some kind of information out of it. So a small data set, something that is descriptive of that specific molecule or that specific fragment. And that new data that we gain from that, we feed back into the already existing data pipeline that is there. So obviously in R&D, everywhere there are data pipelines already ready that are being used today that use ML. And what we basically do with that approach is find some more information that we can feed into that data pipeline to gain better predictions, gain better simulations, gain something that helps us really make better predictions. And that was, in general, on a high level, the approach that we used, and where really the fundamental positive or the fundamental benefit of that approach is that in HPCs, we have a lot of roadblocks in regards to simulations. So how much we can simulate on a microscopic level, how much we can simulate the interactions of specific molecules, of specific atoms, and what that means for those specific molecules. Now, the roadblock there is really that we have the HPCs are heuristic in nature. The simulations are not really scalable, especially if we start thinking about bigger and bigger models, bigger quantum systems that we want to simulate. So not only simulating specific molecules, but also simulating a bunch of molecules and their interactions with each other. And quantum, because of it being exact, is hopefully, or that is the idea, would deliver some better solutions. And then especially once we can scale the hardware a bit more, really get to the parts where we can simulate some of those bigger quantum systems, which then HPC won't be able to do anymore. And that was the approach that we used and used together with GSK. And the project with GSK was about the reactivity of targeted covalent inhibitors, which sounds like a word salad to everyone who is not in the life sciences sector. But for everyone who is in the life sciences sector, they know that this is a very day-to-day process in that sector, which is basically predicting how specific molecules will interact or bind themselves to the proteins in our body. And the idea being we want them to bind themselves to those proteins that make us sick and leave all the other proteins alone. So that's a very general process that there is in the life sciences sector. We use this approach to really see if our approach works, if we get good results out of it, and if we can actually simulate some of those behavioral data on quantum circuits. And that was the outcome of really this project, was the proof that this end-to-end approach works and that we can make meaningful predictions with it. And more so, what was very interesting is that we actually gained some feature set that had value in describing the behavior of specific molecules. So what happened was that there was an existing algorithm that GSK used to classify or cluster their molecules. So the quantum chemist at GSK knew that two molecules had the identical behavioral data. But because they were made up of fully different components, their already existing algorithm would cluster them into different clusters. So interestingly enough, when we ran that same algorithm with the adding of this quantum feature set that we gained out of our simulation, it actually clustered those two molecules together. Now, obviously, that is something, so this simulation can be done on classical computers, so that's why we can't, or nobody can right now claim quantum advantage. But what is very interesting is that this thinking about it from a quantum perspective allowed us to really zone in onto a specific part of the molecules, a specific fragment of the molecule that is very predictive of the behavior of how those molecules interact, and which then now can actually be used in a classical data pipeline. And that is also something that with that approach, with the end-to-end approach, it allows us to really be very hybrid, to even think about how we can better the already existing classical approaches, and at the same time create something that is very scalable in the quantum approach, and then hopefully with time be able to bring that into an actual end-to-end pipeline and make it work in a day-to-day process. And that is basically where we ended our project with GSK. Obviously, there is still ongoing work there, but what is interesting and what I do want to mention before I end my presentation is that when we came up with this approach, what we did is we started thinking about what are the use cases? Where can we actually use this? So when we were doing that, we came up with a bunch of, obviously a huge list of possibilities, but then we broke it down to like the 5 main ones that we were really interested in and we wanted to really explore. And those are the 5 that you see. So GSK was the first project, and what we had thought about was like, okay, after that we'll go and try to do the second project and so on. Interestingly enough, even though the project is just, I think the publication was about 2 months ago, we have already now ongoing projects in all of those fields except for one, which I think is a testament to the idea of really thinking about end-to-end approaches and thinking about how can we actually create something where we see an actual pipeline, an actual roadmap to how it will be beneficial, and then using this approach-centric view to actually find the use cases. So instead of coming from the use case side, going to an approach, going from an approach side, finding a good approach, finding an approach that has value, and then going to the use cases. And with that, I really want to end my presentation and want to ask for collaboration, because we are very aware that there is a lot of research still to be done. We are also very aware that this field is huge. There is so many interesting opportunities, interesting projects that one could think about, interesting use cases, and we want to work together with as many companies as possible to really start thinking how we can better that, how we can also optimize this approach, and how we can get to better solutions. So with that, I'm happy to connect, and thank you very much.
Thank you so much for your talk. Thank you so much for all your insights. I think there's time for a few questions. There's like, I think around 3 minutes. So if anyone of you wants to ask a first question, please feel very free to do so. I have a microphone here. Who has a question on this? Maybe on the drug discovery part of the presentation, or on the end-to-end approach? Nobody just yet. Okay, maybe I have a question. Maybe I have a question regarding the use cases that we were mentioning, into looking into different verticals. Can you maybe say a bit more about kind of which verticals you see in terms of maturity, in terms of kind of also collaborating with them? So like how does the process look like that you know kind of decided to go into life sciences first? How is the future looking?
Yeah, as I mentioned, I think there is a lot of industries that are very reliant on chemistry and on chemistry use cases. And what we really did was look at the most relevant ones, the ones that really build something that today we want to find solutions for. So the ones that were mentioned were, for example, a battery design. It was like carbon capture and storage. So those are the kind of use cases that are very relevant and that play a big role in even sustainability questions. So obviously we are also as a company very much have like this sustainability approach to a lot of our projects. So in that regard, we really started thinking about where is the most value and what is some of the use cases that are more interesting that are out there. And that's where we basically came up with those verticals that we're going to go into. And I think that is also where the company and the partners that we have are most interested in those use cases that are relevant today and that all of us want to find solutionings for.
I see. Thank you. One more chance for a question regarding this talk. Not yet. Okay. Well, let me look at the time if there's... So I think we're actually good to go. Thank you so much again for your talk. Thank you again. I think also you're around on the conference.
Yes.
For the coming hours, or the coming